This week we're going to talk about plasticity, measurements on soil, and these tests are called the Atterberg limits. They're the liquid limits and the plastic limits of soil. So to classify soil in the USCS and the AASHTO systems, like we've been talking about throughout the semester here, we need to know two properties of the soil. Right? We need to know the gradation and its plasticity. And we know gradation now. We've done that in three different tests through a wet sieve analysis, a mechanical or a dry sieve analysis, and then the hydrometer analysis on the fine soil. Next we're going to look at plasticity, and plasticity is a way to quantify essentially how much clay is in your soil by performing two different tests and measuring specific moisture contents um, at different behaviors of that soil. In plasticity, the test measures how much water a soil can absorb as it goes through transitions here. And it's before it transitions from a dry solid to more of a plastic material, something similar to like a silly putty or a Play-Doh. And then as it increases in moisture content, as it would transition phase from a plastic then to a liquid material where it would start to actually flow like a fluid. The definitions to cover here this week are your PL, your plastic limit, and that's the moisture content or the percentage of water that the soil can hold when it can be rolled to a plastic thread without crumbling apart. The liquid limit, the LL, is the percentage of water that the soil can hold right when it starts to flow like a fluid material. And both of these two values, or the PL and the LL, are simply water contents, right? It's the water content of the soil when it's behaving according to these properties. And it's the same way we've computed water content now since January, where we take a wet soil sample, we weigh its mass wet, we throw it in the oven, we weigh it dry, we determine how many grams of water have burned off, and the mass of the water divided by the mass of the dry soil that remains is our moisture content. So it's the exact same calculation that we've been doing for several weeks now. Once you know the PL and the LL of a soil, you can determine its index number or the plasticity index, and it's simply the liquid limit number minus the plastic limit number. These PI values down here, these are approximate ranges that give you a general classification of that soil. If you have a low PI, a low index number, you have a non-plastic soil. So basically you have sand. And if you have a very, very high number, greater than 35, basically those are percentage points of moisture between your LL and your PL values, you have a highly plastic soil, or essentially that would be clay. And everything in between here is some sort of mixture of those textures, you know, loam, silty loam, sandy clay, something in there. Typically, when your soil is dry, a non-plastic soil like sand is very weak, and you're familiar with this because you can walk around a beach and pick up dry sand in your hand and it falls right through your fingers. A highly plastic soil, or like a pure clay, when it's dry, it's extremely strong, right? It's stronger than concrete. The only problem with clay is you can't guarantee that it's going to stay dry on a construction site throughout the life of a project. And once it becomes wet, it becomes unstable and unpredictable. So even though it's strong in a dry form, we really don't want it on a construction site for most applications. This isn't terribly relevant to the Atterberg limits, but I do like to always draw attention to the term soil liquefaction this week. And soil liquefaction is a condition attributed to soil when it undergoes kind of a phase transition, and it usually results in catastrophic changes And it seems like every spring you hear about some kind of disaster caused by liquefaction in California, or somewhere on the west coast where they get a lot of moisture. And it occurs when a saturated or partially saturated soil substantially loses strength and stiffness in response to an applied stress, such as an earthquake. All right, and when that happens, it flows like a liquid. And we know these to be mudslides and landslides. And this first picture was in Washington State a couple years ago. The second picture is just something I found online somewhere, and it was actually a mine disaster, not in North America, somewhere else in the world. But these are extreme cases of liquefaction taking place where the soil was supersaturated and it no longer acted like a solid or even a plastic. It acted like a liquid. We'd also see this in Montana. These are the famous pictures of the Beartooth Highway back in the mid-2000s, where on an unseasonably wet spring, tremendous runoff caused these washouts and then liquefied landslides that took out the Beartooth Highway all the way down through those switchbacks. And it's been repaired and replaced with retaining walls. And I think the idea is this is not going to happen again, but there's a lot of force here. We can only do so much to prevent stuff like this. So a soil phase diagram is basically kind of an attempt here to show soil as it transitions from a dry phase, right, where it would look like a solid block or a brick. And then as if we look down here, the blue scale here, we're increasing moisture content. So we're dry down here at 0% moisture content, right? And as we increase to the right, we're going higher in moisture content up to and exceeding 100%, right? Because you know from prior tests, a pure clay can well exceed 100% moisture content. So there really is no end limit here to this side of the scale. But if we increase from 0% from a dry condition, we'll eventually start to act more like a silly putty, right? That Play-Doh phase of our soil. And when we begin to act like that plastic, we call that the plastic limit, right? The plastic limit is the water content at which we start to act like that plastic. And then we can continue to add water and still remain that kind of silly putty Play-Doh condition until we reach what's called the liquid limit. And the liquid limit here, right, is the water content now where that soil is no longer going to maintain a solid form and it's going to flow like a fluid. And if we continue to add water after a soil has reached its liquid limit, we basically become unstable and almost soupy. The difference, right, this range in water contents between your liquid limit on the high end and your plastic limit on the low end, that's your plasticity index, or your PI, right? And it's simply this number minus that number. There's a couple other phase transitions here that we're not really going to worry about as far as any tests or in our lab, but between the dry phase and the plastic limit of your soil, you have what's called a shrinkage limit, and it's the water content point at which the soil will dry out, but it's going to maintain its shape without cracking, right? Everybody's familiar with seeing kind of a cracked clay dry soil that's been baked in the hot August sun, and it almost looks like that alligator skin. And that soil has exceeded its shrinkage limit moisture content, kind of gone up into here, and then dried out and gone back to dry, and it caused cracking. Whereas if you don't over water your soil, you get it wet just up to that shrinkage limit, it'll come back to dry, and it won't basically lose its integrity or lose its strength, because a crack is a fault line, and a fault line is basically a stress fracture where strength is lost, just like it would be in a bone that you break in your body. On the other end, after you've exceeded the liquid limit and you continue to add moisture, eventually your soil will hit a moisture content somewhere down here on your scale at which it's reached its functional limit. And when moisture exceeds the functional limit, it's basically soup, and there's nothing really useful about soil in that condition. The names, I guess, attributed to the soils in these phases are: you have a brittle solid when you're dry, you have a semi-solid before you reach the plastic limit, and then you're plastic throughout your plasticity index. You become a viscous liquid, right? Viscosity is a measure of a resistance to flow, so you're not quite flowing yet, but you're acting kind of liquidy after your liquid limit. And after the functional limit, you're a mess. You're a liquid soup. And if we look at that same water scale here, where again 0% moisture content's on our left, and we're increasing water content to the right here, these are where you would fall along that moisture content scale on two different types of soil. If you have a sandy soil, your plastic limit's going to start really close to 0, because if you remember from the very first lab, the texture test, you did not have to add a whole lot of water to a sandy soil to try and start making that ribbon, right? You can mold it and form it into that kind of a plasticky condition with just a little bit of water. And as you add water to that, really quickly, you're going to reach its liquid limit. You're going to, and then blow right past it, because sand will become very unstable very fast. Much different than clay, right? Starting at 0 here again, you have to add a lot of water to clay until you get it to reach its plastic limit. And then water will continue to take on a lot more, clay will continue to take on a lot more water, and take it on and take it on and take it on before it ever reaches that liquid limit, right? You're greatly going to exceed 100% moisture content before you get clay into its liquid limit. So if you have a sandy soil, your PI range is going to be really small, really narrow, and you're going to be shifted down here closer to the 0 region on your moisture content scale. Much different than a clay soil, you're going to have a wide PI range, right, greater than 35, and you're going to be shifted a lot higher away from 0% moisture before you even begin your plastic limit. Most soils are not a pure clay, they're not a pure sand. You're going to be somewhere in here, in this kind of moderate range. And the two tests that we use to determine the plasticity index, I call them the worm test for the plastic limit and the dish test for the liquid limit. And we'll look at the plastic limit test first, right? That's what we call the worm test, and the tools are pretty basic. You need a little dish to mix up some soil and water, right? And you want to take that moistened soil and form what they call it an ellipsoidal mass, basically a little ball of soil in your hand. And you're going to take that ball and you're going to roll it out into a worm. And the surface that they call for in the test is a glass plate, because it's textured and it'll start to pull moisture out of the soil. Honestly, I think paper works even better, so we use some heavy stock paper, and the paper fibers suck that moisture out of the soil really nicely as well. But you don't want to use a lot of pressure, right? You just want to have enough pressure to roll this back and forth until you can get this worm down to 1/8 of an inch diameter. And if you can attain 1/8 inch diameter before your worm starts to break up, you haven't dried it out far enough. You haven't dried it down to the plastic limit. So you ball it back up and you repeat the process, and you keep rolling this worm down until it starts to crumble and break into pieces before or at the 1/8 inch diameter size. Once it starts to crumble like that, you've forced the soil into the plastic limit condition. and you immediately want to transfer all these contents then into a tin cup and go weigh it wet so you can get your wet mass, and then we're going to throw it in the oven, dry it out, and we'll come back and weigh it dry so that we can compute the moisture content of the soil when it was in that condition, which would be the plastic limit of that soil. And just for an example's sake, as we go through some example numbers here on the next couple slides, let's just say that a particular soil that we're working with was determined to have a plastic limit of 11% moisture, 11% moisture content, right? And you want to do about 3 of these worms on each soil so you can get an average, right? You don't ever want to just trust one data point. You want to get at least 3 so we can get a good consistency and agreement and get an average. The liquid limit test is a little more involved, but still not difficult. It uses this dish here. This is an Atterberg Limits dish. And this dish has a crank, and that crank is attached to a little cam that raises and lowers. It doesn't lower, it raises this dish, and then the dish falls by gravity and makes an impact or drops back against this base. And every time that dish falls to gravity and impacts this base, it creates a little bit of energy and vibration. So same thing, we take a little dish, we mix up our soil into almost like a peanut butter consistency, like you can see in this picture. And then we smooth it into the dish apparatus. And once you've smoothed your soil about 1/4 of an inch thick in your dish apparatus, you're going to take a grooving tool and cut a groove so you split your soil into 2 sides. There are 2 different grooving tools to use. In this picture you can see this kind of a flat, almost like it's just like a little wedge. This is the specified groove tool when you're following ASTM testing procedures. If you're following AASHTO testing procedures, this is the groove tool that they use. We have both of them. I actually prefer this AASHTO grooving tool. It's like a little, you can see a little triangular wedge, and it's just easier to cut your soil. So we have a couple of both. The height that the cam raises this dish is 1 centimeter, and this AASHTO groove tool has this block on the handle which is exactly 1 centimeter, so you can adjust the cam on your dish to make sure the height is calibrated correctly. The AASHTO groove tool doesn't have that, so you have a little 1 centimeter block to accomplish the same thing. But whichever groove tool you're using, all right, you'll cut your soil into half, and then you're going to start cranking this handle on your groove tool, and you're going to count the number of drops or the number of impacts that it takes this dish to get that soil to close back in on itself over 1/2 of an inch distance. And once that soil has closed back on itself and it touches again over 1/2 of an inch, you immediately want to take a sample of that, throw it in a tin cup. We're going to weigh it wet, throw it in the oven, and then we're going to weigh it dry, again so that we can compute the moisture content of the soil when we counted the certain number of cranks. And then we're going to repeat that process 3 to 4 more times. Each time we're going to add a little bit more moisture to our soil so that we're increasing its water content, we're making it a little more liquid. And in theory, then if you have a soil which water content's a little higher, you cut this groove, it's going to flow more easily and it'll take fewer cranks to get this 1 inch contact again. At each time, you take a sample of that soil, you put it in a tin cup, you weigh it wet, and we weigh it dry. And we want to have a series of data points. 5 data points are going to have 5 different moisture contents, and hopefully 5 different numbers of cranks that it took to get that soil to close back on itself. And the liquid limit is defined as the water content at which it would take exactly 25 cranks to close. and it's not likely that one of your data points will be exactly 25, right? Here's just a example of 5 data points that come from a dish test. And if we say our first trial took 55 cranks or 55 blows, and we determined the moisture content by weighing our masses wet and then dry to be 4% moisture, we'd have a data point that we can plot on our graph. And a copy of this is included in the lab manual, where we have 4% moisture on our vertical axis and 55 numbers of cranks, or number of blows, with that dish. When you look in your lab manual, you'll see that I have the moisture content scale blank. It's because I don't know what soil you're going to use, and I don't know what moisture contents you're going to be seeing. So you're just going to set your minimum is 0% moisture content. You're going to set your maximum to accommodate whatever moisture contents your particular soil had, and then you're just going to proportion those numbers out evenly along this axis. You plot all your points. You want to have at least 5 so that you've got enough redundancy or ability to throw out a bad outlier or data point if you happen to have a data point that just doesn't look good. So if we've added a little bit of moisture, it takes fewer cranks, so 42 blows at 25% moisture content would plot us here. Third data point would be 32 blows at 17% moisture content, 20 blows at 28% moisture, and 9 blows at 30% moisture content. And generally this is the trend you want to see in your data points, is starting low on the right and increasing going to the left. And you can see here, this second data point looks like it might be a little suspicious. It looks to be an outlier, right? These other points generally form a trend line, and if this is the case, you've got the ability to just throw that data point out because you have reason to think it's not consistent with your other data points. And if you only had 2 points or 3 points, you don't have that luxury. So that's why we try and do 5 to even 6 specific data points for this test. So you put a trend line in through the good data points, and then your liquid limit is simply the water content at which it would take exactly 25. So because we have a trend line here, we can interpolate that value, and we would come up at 25 on our number of blows scale until we intersect our trend line, and then we'd come over and read the water content on our vertical scale. And in this data set, it would be approximately 23% moisture content when it would take exactly 25 blows. So the plasticity index of the particular soil in this example, again, is your liquid limit, which is this dish test, minus the plastic limit, which was the worm test. And if we had 23 for this dish test, and we said a couple slides ago we had 11 for the worm test, your plasticity index for this soil is 12. And it's a lot of work to get to this number, and this value is needed next week when we run through the AASHTO and the USCS classification charts to actually classify soils with gradation results as well. One last thing to mention here. When you're performing the worm test, right, your goal is to get soil specifically to this moisture content. And we want to start out on the wet side, right? You're going to over wet your soil a little bit so that it can form a ball, and then you're going to essentially dry your soil out, right? The rolling action, creating that worm on paper, dries your soil. It removes moisture. So what we're doing with the worm test is we're starting out a little wet, more wet, and we're drying ourselves down exactly to the plastic limit moisture content. A little different than the dish test. With the dish test, we're trying to achieve this liquid limit, right? That's the interpolated value of 25 cranks. We start out with our soil drier than the liquid limit, and that's why the cranks usually take 40, sometimes 50, or even 60 cranks in the first trial because our soil is pretty dry. And then we're going to be adding water throughout the test with our 5 or 6 data points, and we're actually going to over water it, and we intentionally want to go beyond the liquid limit, right? So that these last couple data points out here are when we have a high moisture content and the number of cranks of our dish might be 10, might even only be 5 cranks. So we're not stopping exactly at 25. We're actually going to intentionally go past it. We'll work on these two tests this week, and then next week we'll use the gradation results and these results and learn how to classify based on the USCS and the AASHTO systems.